All right, so let's move on to talk about when does a function not have a derivative at a given point? Okay, so there are a couple of situations here. As you can see, first of all, when you have a corner like this, okay, when you have a corner, and why they do not have a derivative, because remember guys, when we're talking about the derivative, that means the slope of the tangent line at a given point exists, right? But you can think about this, at this specific point, it's impossible to have a slope of the tangent line, because if I standing at the point through this way, I'm gonna follow this train. However, if I starting from this part, the slope of the tangent line gonna behave like this, right? As you can see that, guys, the limit from the left hand side does not agree with the limit from the right hand side. So at this corner situation, and similarly, when you have a cusp, the slope of the tangent line also does not exist, right? Because it's kind of like it become very, very crazy. You can from one side it goes to the slope might be a super large positive number, and if you do from this way, the slope of the tangent line is a super small negative number, like -1000. Hence, the derivative does not exist. And there is another situation, if you have a function like this, and then at this specific point, you have a vertical tangent line, and then that slope also does not exist, and then the derivative does not exist at this point, okay? So those are the first three situations. Number 4, any discontinuity. We have the jump, we have the removable, and defined at this point is also not differentiable, or the derivative at those points does not exist. And there's also another situation, if you have, let's see, this is 0, and at around 0 you have crazy oscillation, so the derivative at x equals 0 is also not does not exist, and the function is not differentiable, okay? And there is a very simple but powerful theorem which is differentiable can give you continuous. Meaning, if a function it is differentiable at a point, you can definitely get the conclusion that the function is continuous at that point, okay? So if f prime of c exists, then f is continuous at x equals c. But the other direction is not true. As we will see from the first three situations, right? It's all continuous, there is nothing wrong with that, but the derivative does not exist, okay? So we complete section 3.2, and then I'll see you in the next section, okay?